Indeed, we can find neurons that are sensitive to motion in the area MT of the monkey's brain. So these neurons are sensitive to motion. So here on this graph, you see the activity of such neuron in the area MT, and you see the activity of this neuron is indicated by the black dots, and it is proportional to the amount of dots moving in the same direction. So the more dots are moving in the same direction, the more this neuron is active. So actually, in this graph, you can also see the performance of the task. So white dots represent the proportion of the correct responses. So actually you see a perfect overlay, perfect match of the behavior of the monkey and of the neuronal activity. So here, neurons in the area MT are perfect motion detectors. The more motion in specific direction is present on the screen, the more these neurons are active. So you can find neurons in this area that are sensitive to left motion, to the right motion, to any kinds of directions. And these neurons are simply detectors of motion. So they collect evidences for motion in certain direction. Okay, there are some motion detectors in the brain, but how the decision is made by the brain? So let's make a look to the model, diffusion model, explaining the decision-making process. So first, information is collected by the motion detectors. So in our task, some neurons are sensitive to left side motion, some neurons are sensitive to right side motion. So these neurons are activated by a motion presented on the screen, and the activity of these neurons is proportional to the amount of dots moving in a certain direction. At the next stage, this information is integrated by other neurons, and as we will see, these neurons are located in the area LIP. So activity of these neurons actually represents the integration of the sensory information over time. So activity of these neurons gradually increases over time, and whenever the activity of these integration neurons, of integrators, crosses the decision threshold, the decision is finalized, and this information is sent to the motor neurons, and these motor neurons actually switch the gaze in the specific direction. So at the same time, these integrators, these neurons integrating information from the detectors, inhibit alternative decisions. So they make inhibitory projections to the alternative decision-making neurons. And actually, this network compares evidences for the alternatives. So if their integration or integrated neurons getting information from the left motion detector increases activity till a decision-making threshold, it will at the same time inhibit alternative decision and activate motion switching of the gaze to a certain direction. It will send information to the brain area, frontal eye field area. And neurons in the frontal eye field will switch the gaze into the specific direction, switch gaze left. So this simple model can actually explain the decision-making process during the perceptual decisions. Let's make a look to the behavior of actual neurons. So diffusion model suggests that this integrator, this decision-making neuron, accumulates information from the motion detectors over time and gradually increases activity. Yeah? So if activity of this decision-making neuron, of this integrator, crosses the decision threshold, the decision is finalized. So next, information goes to the motor cortex, to the frontal eye field, and these neurons in the motor cortex will switch the gaze in the certain direction. So here you see the integration process. Decision-making neurons integrate information over time, they collect information from detectors, and if they do get enough information, if they are activated till the decision-making threshold, the decision is finalized. So let's make a look to the activity of the real neurons. So here you see the activity of the neuron in the area LIP. This is a decision-making neuron. This is an integrator that accumulates information from the motion detectors and integrates it over time and gradually increases activity during the decision. So as you see here, activity of this neuron is gradually increased over time. And if this is a relatively simple decision, activity increases faster as indicated by the black line, or slowly, very slowly, as indicated by the red line. So we see here an integration process. If we will plot all of these graphs, all of these curves, firing rates, relatively to the onset of the decision, relatively to the moment when monkey switches the gaze into a certain direction, as you see on the right side of this graph, you will see that in all trials, the activity of this neuron reaches a decision threshold. At this moment, at this particular moment, the decision is finalized and information is sent to the motor cortex and monkey switches the gaze. So actually, around the decision threshold, we can predict the decision, perfectly predict the decision. As you see here, we see a fundamental process of the decision making. So we see how information is accumulated by the neurons over time. We see that the accumulation of information, activity of the neuron, the firing rate reaches a certain decision threshold. Activity of this neuron can even predict the random decisions. So red curves indicate the activity of the neuron at the most difficult condition when all dots are moving in random directions. So in this case, animal has to switch gaze randomly. Even at this situation, this neuron very slowly accumulates information and reaches the decision-making threshold. Interestingly, we can even electrically stimulate this neuron. We can change the decision of the monkey. So we see here a fundamental process of decision-making. We can summarize it in this graph. So first, motion information is projected to our retina. And next, our motion detectors in the area MT that are sensitive to particular motion are activated. So the information from the motion detectors is collected by integrators, by the decision-making neurons that accumulate information over time and at the same time inhibit alternative decisions by inhibitory neurons. And finally, if the activity of the integrators of these neurons in the area LIP reaches a decision threshold, they activate neurons in the frontal eye field, and animal switches the gaze in a certain direction. So it's a relatively simple model, but it actually explains perfectly well the decision-making process. So why do we need these three important stages for the decision-making process? So indeed, first, the motion detectors accumulate sensory evidences for the alternatives. Next, decision-making neurons in the LIP area integrate this information over time. And finally, the evidences for the alternatives are compared. And if this critical difference for the evidences in line with the alternative A or alternative B crosses the threshold, the decision is finalized. We need these three stages to actually cope with the noise in our sensory processing. Simply, sensory evidences for alternatives are normally quite noisy. So it makes sense to integrate this information in the decision-making neurons, for example, in the area LIP, to integrate it over time and remove noise from the sensory evidences. Next, we simply compare the evidences for two alternatives, and if this difference reaches a certain threshold, we finalize the decision. So this network of neurons basically accumulate information for decision A and decision B, and if the evidence for certain decision crosses the decision threshold, the decision is finalized.